All right, thank you everyone for being here. This is Gero from Murata, Senior Product Marketing. My name is Oriol Chavanel. I'm Ecosystem Tech Lead at Submer, and we're going to present the workstream of power distribution in immersion. As you can see in the subtitle, basically is a summary of the single-phase immersion tanks and how we can integrate one of the specifications of OCP, the Open Rack version 3. So in the workstream, we are counting with a lot of people from the power perspective and from the immersion perspective. And our objective is how we can make this work in immersion as it works vertically in an rack. So at the moment, we are already in a specification document, that we are drafting with the community. So we are touching on all of the elements that are required to provide a full solution that works in single-phase immersion tanks. These are generally divided, but what it goes from the single-phase immersion tank to a busbar, a power shelf, a power supply unit, the tests that Amy was just mentioning before, failure mode testing, all of the elements that are even the fuses that are now part of electronics into the vertical air racks, but that in immersion they can change or they can operate differently. The end goal is, of course, to provide a solution that works good in immersion. It has some other efficiencies compared to air, and that's all the work that we are doing within the team. So here is an example of speaking about the tank now, the tank references that we have been using with the community. So there is, of course, a lot of information based on the immersion requirements data sheet and Excel that we are using for this. There is, of course, a lot of the FMEA that Amy was presenting just before. There is a lot of the community feedback that we have been gathering, and a lot of the HRI or the UL rule that is also about insulating fluids in immersion. As you can see in tank references, we're speaking, or we are trying to make this as flexible as possible for all of the tank vendors in the market. So considering that any sizes, any way to implement the busbars, the stoppers, the safety is open enough, so it can be adopted while we are, of course, considering that all of the elements are well implemented and they are not, of course, causing any risk or any malfunctioning into the immersion single-phase tanks. This is, for example, some examples that we were discussing over this last half of the year about how we are distributing the weight over the immersion tanks or the connectivity with the busbar, as well the short circuit prevention. So as you can see in the images, basically, it's very important that the weight of the IT hardware or power shelves that are installed in the tanks, it's stopping properly. It's relying into stoppers into the lateral sides, up, down, wherever. This is just some examples. Then there is, of course, the short circuit prevention. The design of the RV3 busbar compared to the Open Rack version 2 busbar is way better. So you need to think that in a tank, the gravity, of course, goes downside. So if we drop something into it, it may fall into the busbar. It can cause a short circuit, but it is preventing this because of its new design, where the positive and negative are completely different than before. So all of these things are things that we are discussing, that we are doing into this work stream, and that are very important to define, at least for the tank references. Here you have more examples. For example, the fluid convection, how the temperatures are being studied for the busbars. You will see later on with Kevin when he will speak and touch on the power, more specific side of things. But the advantages of the busbars in immersion by itself are that we can take way more, a lot of them, right? So if a busbar is designed to handle 150 amps, for example, we can minimum take double of it in an immersion tank because it's actually installed in the bottom of the tank, and that's typically the part that is better cooled, where the fluid is more cold, and from where we can deliver the most. So now we are having, of course, a lot of water-cooled busbars. We're having the HPR busbar from Meta. We have a lot of ways to tackle this heat increase, sometimes with more copper, sometimes with water. Well, in immersion at the moment, we don't need to, let's say, modify or over-engineer anything. Just as it is now, it's good enough. And that's actually a lot of the testing that we have been doing as of today. Another important thing about the tank references that we have been discussing into the work stream is the polarity that we need to consider. Everyone knows how to install something in a vertical rack because it can only go one way. But when we look it horizontally, looking from up on it, we can have problems with the positive and negative. So this is something that we also have been discussing and agreeing. So there is no unexpected issues or people frying €1 million servers, for example. So this is very important, where the positivity goes, where the negative goes, how the busbars are installed. And here you can see also a graphic, an image that shows how this amperage delivery into the busbar is well distributed if the power shelf is, for example, installed in the center. So then it goes left and right on the same way. I will switch to Kevin now. He will tackle a bit more into the power part, about the power shelf and power supplies. Kevin, all yours.
Okay, so what we wanted to do was make this as flexible as possible, but put guardrails in, put requirements in, things that we need for use in immersion. We also wanted to be able to be, for vendors to be able to be creative, to come up with more power, come up with different ways of doing it, but just put the guardrails in. So what we've done is we've looked at it and said, okay, these are the things we need to do. We have to put handles on these. This is a 3OU shelf that we have here a picture of. When you lift that, when you have all the fluid in it, this one's not working? I'm sorry. I can talk loud anyway. But nonetheless, when you have all the fluid in it, it weighs a lot. So your handles have to be able to support that weight. And so it's a requirement. We're putting a requirement in there for handles. We are also saying we don't want the shelves to be more than 4 OU tall. If you make it more than that, it becomes unwieldy, it becomes dangerous, quite frankly. You make it 1 OU, 2 OU, 3 OU, flexible, again. But we're saying no larger than 4 OU. This is what the community decided, and that's what we're going to do. We're basically using ORV3. We're using that bus bar, and we're using those connectors. So that's the definition today. If things change in the future, we'll deal with it. The AC input connectors and the controllers need to be above the fluid so that the operator is not putting his hands down in the fluid. It's just a best practice. You could put them down there, but it's not what we want to do. We don't want to do that. We want to say, no, it has to be above. So we're doing that. The weight of the power shelf, as Oriol mentioned before, is not to be supported on the bus bar. It's to be supported in the structure. So that's by definition. We're saying it has to be that. In this case, with ORV3, we're using single-phase power supplies. So if you're using single-phase power supplies, you must use groups of 3. The reason for that is it balances the phases. You don't end up with large currents on the neutral line if you're using a Y configuration. So that's what we're doing. Okay, the power supply. Basically, we're utilizing the ORV3 style power supply. So it's greater than 3 kilowatts. Now everybody's coming out with 5.5 kilowatts. Next, who knows? 8 to 12 kilowatts. I've walked around and people have said there's 12 kilowatts. As long as it's above 3, that's the requirement. So whatever people can innovate, we're going to allow it. You can use 51 or 54 volts. ORV3 today requires 51 volts, but to be honest with you, the difference between a 51 volt input to a server and a 54 volt input, there's 11% difference in the bus bar and the connector voltage drop. So when you start getting these higher currents, it might make sense. We're just allowing either, so you can be creative. Basically, you meet the ORV3 specifications, okay? It's that simple. We're not trying to reinvent the wheel. It works very well. We're just putting it in immersion. So there are requirements, as we all know. You have to be compatible with the fluid and that sort of thing. The mechanical handle has to not be in the way. Typically, the way that they're used in the shelves today does work. So let's not, create something new. Basically, the biggest difference between the power supply in immersion and the one in the air is you either remove the fan or you stop the fan, and the power supply has to be able to operate. Of course, right? That's obvious. But that's the case here. It's almost that simple. And what most of us are doing is we're stopping the fan, because that way in manufacturing you can run it through the normal air operation, test it, everything works, then you redo the firmware so that it shuts the fan off and it operates without. Now you're good. Okay. And you know what we've done is the team with Submer and ourselves, we've coordinated together and we've put our shelf in the tank, and then we put loads in there for 54 kilowatts. And what's amazing is the temperatures inside the power supply are so cool. That's not neat, it's low temperature. We don't see temperatures above 60 C, really. And that's nothing. We can operate 130% load and the temperatures are still way down there. That's the sweetheart deal with immersion. That's what we can do. We're actually going to end up pushing this power supply that's a 3.6 kilowatt power supply to somewhere close to 6, 7 kilowatts. The only thing I have to be careful of is the component ratings for the currents, okay? I have to take that into account. We're still got more testing to do, but we've shown that it can be done. As with the bus bars that can handle almost 2 times the power supplies can do the same thing, because the fluid is so efficient at cooling compared to air. It works very well. We also want to be able to be careful about safety. This is an interesting thing because UL and their counterparts haven't quite caught up with us. So what we're doing is we're making sure that we meet all the air requirements, plus we're putting it in fluids and we're testing. And we're making sure that everything still works. All the air requirements allow it to shut down safely. You can't short it out. You overcurrent, it still shuts down. So we're making sure nothing gets changed because we're using it in fluid. But anyway, that's what we're working on so that we can show the agencies, show people, hey, this is what we found, this is what we want, so they can create specific test criteria, because there is none really today. Okay.
Something to add as well to just what Kevin said about the elements distributing the power. There is the power shelf, there is the PSU, but also even the connector or RV3 connector, either for the server or the power shelf, was something that we tested and we showcased. We don't have that much time, but we showcased into the regional summit back in Lisbon this year. And also the connectors can deliver twice of their amperage in immersion. The Molex team actually outside here, they have a booth. They are showcasing that in case you want to step by. But they were also participating in all of this testing, and actually it's very amazing to see that. So just to close up, we have a call to action, of course, for our work stream. As you have seen in the very beginning, we are now in the phase of building the spec. So we are asking for people who has a power background or, of course, immersion tank providers that can work with us and can help us define some of the elements that we still have open. Now we have a very good conversations with the fuses as well. It's a very important topic. As you may know, a fuse can behave very well in immersion and can be completely unproductive because the fuse needs to break when it's at certain temperature, and if it's very well cooled, it may not. So this is something that we are now tackling as well. But on the rest of the elements that you have seen into the presentation, we are already going on the drafting the base spec. Sorry. So this is all of the people that is collaborating with us at the moment, companies and names that are helping us with this document. So as commented, if you have any inquiries, you want to join us, please scan the QR that we just shared here. This is the Power Distribution in Immersion Workstream QR, and please follow us in the mailing list. And of course, I think there is time for questions, so in case anyone has any doubt, please don't doubt going out to the microphone.
I have a question.
Of course.
I particularly like the polarity thing, right? So is there a mechanical means in the spec that prevents you from putting a server in the wrong way around?
I cannot hear all.
Do you have a mechanical means built into the spec to prevent a server from being placed the wrong way around?
Well, in this,
Other than the connector itself in the bottom or the visual indicators, right? If somebody is not paying attention and putting the server the wrong way around, reverse polarity, how big of a deal is that? And is there something in the way to prevent it?
that's a very good question, Rolf. Thanks. Actually, in the next speech, I will be running myself that there is a bit of this information following the immersion requirements Excel, that actually this is a very important part. We are requesting that all of the immersion tanks, they need to have a specification, a logo that it's saying whether it's the positive or the negative. So when you are installing a server or a PowerShelf, you always see what is positive and what is negative. So of course you can put it wrong. You can also put it wrong in there, but at least you have some reference that you know how that needs to be installed. Of course, as I mentioned before, frying €1 million of servers, it's not good for anyone. So knowing where the negative and positive is, it's very important for the immersion tanks. Mechanically speaking, yeah, no, mechanically.
As in air, they don't do it. You could do that. You could do the same thing. It's not. I agree with you. We kind of. I've talked about it with people. We just haven't got it yet. Maybe there needs to be a pin or a fin that, and then you'd have a slot. That could do it. And we're looking for creativity, how we could do that. I don't disagree. Again, creativity, anybody that might have some ideas, but like I said, I think you could do a fin or a pin and have a slot. That would be that's what I'm thinking right today. I'm an engineer, like how all of us mostly here, and that's what come to my mind. But maybe there's a better way. The connector guys too. Any creativity you guys might have? It does. Okay. We'll take that into, please. Well, no, that's good. Thank you. Thank you. Okay. And anybody else, any other idea? Because what we'll do is collect them. Yes, sir.
Actually, comparing to the previous ORV2 busbar, so we've got an improvement with the ORV3 busbar that is preventing most of the short circuits, if something falls, like a screw into the tank. But before, the ORV2 busbar was having one zone upper than the other one, so this was preventing to happen because you could never be able to put positive and negative into the same way. There was always one longer than the other one. Now the ORV3 busbar, it is true that it's the same ways on the both sides, so this can happen. It's a really good idea, so we will of course include for discussion on how we can prevent this happening in immersion tanks as well. Yeah. Thanks.